Okay, so let's talk about improper integrals a little bit. What I've got up here is a graph of the function y equals 1 over x squared. And you notice I've colored in an area of the graph below the graph of the function, y equal 1 over x squared, and over the half line from 1 to infinity. That's what that red stuff is right there. Now that may be an infinite area, but in fact, as we'll find out, it may be finite. The question is, if that were finite, how would we evaluate that and make sense of it? So, what did I just do here? Okay, so how are we going to make sense of this? Well, let's go over here, and if this was just an interval, right, if we were looking for the area under the graph from 1 to 2 of 1 over x squared, that would just be the integral from 1 to 2, right, of 1 over x squared dx. However, we're looking at the area under the graph over the interval from 1 to infinity, so it'd be nice if we could call it the integral from 1 to infinity of dx over x squared. Of course, the fundamental theorem of calculus does not deal with that. So how can we make sense of it? Well, the idea is if that area is finite, then as I bring my t, if I bring points out here and look at the interval from 1 to t of that function, I'm going to approximate that area. And if I take the limit as t goes to infinity, I should get closer and closer to that area. So we're actually going to define that integral, the integral from 1 to infinity, to be the limit as t goes to infinity of the integral from 1 to t. And we're going to define that to be the case if that limit exists and is finite. If I say is finite, that implies it exists, right? So otherwise, we'll say it diverges. In this case, we say it converges. Otherwise, we say it diverges. Okay. So you may wonder if any of these things ever converge, if we can ever get a finite area under an infinite interval. And the answer is yes. In fact, this particular one we're looking at converges. So let's evaluate that. This function is continuous on the interval from 1 to t, so I can use the fundamental theorem of calculus to evaluate the integral from 1 to t. So that's the fundamental theorem of calculus I'm using. What does that mean? That means I'm going to evaluate it by finding the antiderivative, right? And the fundamental theorem of calculus says if I can find the antiderivative, if the function's continuous over a closed interval and I can find the antiderivative, then I can evaluate the integral by plugging the endpoints into the antiderivative. And I'll let you double check that the antiderivative of 1 over x squared is negative 1 over x. And so this is the limit as t goes to infinity of negative 1 over t minus negative 1, so that's plus 1. So what happens here? Well, this first term here is of the form negative 1 over infinity, right? That's a limit form. That's not an answer, but that's a determined limit form. It goes to what? Yeah, it goes to 0. So that means the whole thing is going to go to 0 plus 1, which is 1. So this area here that we were just looking at happens to be 1 square unit, that area that it goes up infinitely far. It's definitely finite. This integral here converges. So let's sort of summarize what we call type 1 improper integrals. That's integrals like this. So there's actually 3 types of type 1 improper integrals. Let's try a different color here. Let's do green. So the first one is the one we were just looking at. It is integrals of this type from some finite number to infinity of f of x dx, and we define that to be the limit as t goes to infinity of the integral from a to t f of x dx, if that limit is finite. Otherwise, we say it diverges. Okay, so what is the other thing we can have? Well, let's try a different color here. Let's try more of a blue. What do you think? We could have the integral from negative infinity to a of f of x. Oh, I needed dx there, so sorry. Of f of x dx, where a is some finite number. Of course, that's defined to be, I bet you can guess this. It's a limit as t goes to negative infinity of the integral from t to a of f of x dx. And the same conditional here gets added here, right? If that limit is finite. In other words, we say diverges. Okay, and finally, how are we going to define, what else can we have? Well, we can actually have an integral from negative infinity to infinity. And in order to figure that one out, we're not going to take that as a limit right away. We're going to break that up. And just like you can break up, regular integrals with the function continuous on a closed interval, we're going to say for any point A, if it's the case that this breaks up into two of the other types of improper integrals, the integral from negative infinity to a of f of x dx, and the integral from a plus the integral from a to infinity of f of x dx, and both of those integrals converge. So that the integral from negative infinity to infinity is going to be the sum of these other two improper integrals if both converge. Otherwise, we say it diverges. If one, that means if one of those two integrals diverge, it diverges. Okay, so before I stop this recording, this gives us a definition. Let me just point something out. If f is continuous on every interval from a to t, where t is bigger than a, then the second integral here, when we look at this limit in this first case, we can evaluate that using the fundamental theorem of calculus, and that's the idea. And if f is continuous on every interval from t to a where t is less than a, then again we can evaluate that limit, that second integral, the limit from t to a of f of x dx, using the fundamental theorem of calculus, that is finding the antiderivative. And if f is continuous on the entire real line, it turns out you can break it up at any point and you'll get the same answer here. And we can, well, if it's not continuous, that's where the issue is. That's where the type 2 improper integrals are going to come up. Okay, and I wrote that as integers, and I meant integrals. So let's fix that and stop.